The last theorem that we're going to talk about that relates the roots of a polynomial is called Descartes' rule of signs. And this is named for René Descartes, who's a famous philosopher and mathematician. You've probably heard of him. If you've ever heard of the Cartesian plane, that is named for him, and that's just another way of expressing the coordinate plane. Descartes was actually the person, or is the person credited for coming up with the idea of plotting points on a coordinate plane. So he did a lot of important work in mathematics, but this rule of signs work is what we're talking about right now. And what it does is it tells us the number of positive real roots or negative real roots that our polynomial could have based on the signs of the coefficients in our polynomial. When we're using Descartes' rule of signs, we need to look at the positive real roots and the negative real roots separately. And all I mean by that is we're looking for the positive roots, meaning the positive values of x, so the positive x-intercepts of our polynomial, or the negative x-intercepts, the negative roots of our polynomial. In order to determine the number of positive real roots for our polynomial, what we do is we're going to look at the number of sign changes between consecutive coefficients of our polynomial. So we look at our polynomial, and we're going to make sure it's in standard form, meaning that we start with the highest degree term, and all of the terms are written from highest degree down to lowest degree. And then we're going to look at the number of sign changes between consecutive terms. So whenever a term changes from one being positive to the next one being negative, or vice versa, we count that as a sign change. The number of positive real roots in our polynomial is going to be equal to that number of sign changes, or it could possibly be less than that number, but if it is less, then it has to be less than that by an even number. And we'll talk a little bit about why it has to be less than the number of sign changes by an even number in the next lesson when we talk about the fundamental theorem of algebra. So to find the number of possible positive real roots to our polynomial is pretty simple. Take a look at your polynomial, count the number of sign changes. The number of sign changes is the maximum number of positive real roots. If it's less than that, then it has to be less than that number by an even number. To find the number of possible negative real roots, we're going to use the same idea, but this time, instead of looking at the polynomial p of x, we actually need to plug negative x into our polynomial. Once you plug negative x into your polynomial, you want to simplify your polynomial and see how the various terms behave. Look at the sign changes here. So once you've simplified your polynomial with negative x plugged in, you count the number of sign changes just as before. The number of sign changes now represents the largest possible number of negative real roots, and also as before, you could have less than that number, but it must be less than that by an even number. So time for an example. Okay, so we want to identify how many real roots the polynomial 2x to the fourth minus x cubed plus 3x squared minus 1 has. So like I just said, we need to do this in two steps. First, we're going to look for the possible number of positive roots. And this is slightly easier because we already have our polynomial written in the form p of x. That's what we're given. So what we want to do is we want to identify the number of sign changes in our polynomial. Well, our polynomial starts out positive and then goes to negative. So there's one sign change. Then we go from negative to positive. So there's two sign changes. And then we go from positive to negative again. So we actually have three sign changes in our polynomial. That means that at most we could have three positive real roots. If we don't have all three, then the only other possibility is one real root. And the reason it can't be, or the reason it can only be 3 or 1 is that, as we said before, if it's not the full number of real roots that we found, then that number can only be reduced by an even number. So we could have 3 real roots or 1 real root, because we would have reduced 3 by 2 to go from 3 to 1. But it's not possible to have only 2 real roots, because that would reduce 3 by an odd number, which doesn't work. And again, I'll talk about why that is in the next section when we talk about the fundamental theorem of algebra. We also have to have at least 1 real root, because if we reduce 1 by another even number, that'd be 1 minus 2, that would take us to -1. And to say that we have a -1 real root to our polynomial doesn't make any sense. So we have to have at least 1 real root. Now we need to find the number of possible negative real roots. Negative real roots. Now to do that, we need to evaluate our polynomial for negative values of x. So I'm going to plug negative x in to the polynomial. Each place that I see the variable. Sorry, this has to go on multiple lines. And then we need to simplify this. Well, negative x to the 4th is just going to take us back to a positive x, since we would be multiplying a negative number 4 times. So that's going to reduce down to 2x to the 4th. Negative x cubed would end up being negative, and since we're subtracting that, that term's going to end up being plus x cubed. Negative x squared will of course become positive, so that next term is just 3x squared, and then we have -1. So you can see that our polynomial, when we evaluate it for negative x, is a bit different from what it was for a positive x. Now we need to go in and we need to count the number of sign changes that occur. Well, our polynomial starts off with a positive 2. Then the next coefficient is also positive, as is the third coefficient. And we don't end up with a sign change until we get down to the constant term. So in this case, there's only 1 sign change, which means there can only be 1 negative real root to our polynomial. And because there's only 1, that is the only possibility. We have to have 1, because if we reduced 1 by an even number, like I was saying earlier, that would give us a negative number of real roots, and that doesn't make any sense. So that means that our polynomial is either going to have 3 positive real roots or 1 positive real root, and it must have 1 negative real root.